All right, hello and welcome back to another video. Today I'm breaking down the solutions to the exam questions from the other day. Just a bit behind schedule on those ones, but as you can see that when I work through these, you'll see that each of these questions requires a little bit of working out to solve. So starting out with question one, we need to start by stating the range and domain of these two functions. So this is a composite function type problem. So we need to know what the domain and range of both of these are in order to answer anything to do with combinations of functions. So starting out with this, we have a quadratic, x squared minus 9. The input x can be anything, so the domain is equal to r. So in general, a polynomial will always have a domain of r, unless, of course, it contains a square root. Then it won't be. So now, in terms of the range, let's think about the shape of this graph. So this is a parabola. It has a turning point down here at 0, -9. It's like the y equals x squared graph has been shifted down -9 units. So therefore, the range is going to be all of the y values from -9 up to infinity. So that is what we're going to put down as our range. So it is from 9 up to infinity, and we are including 9. So it's perfectly acceptable for us to get 9. If I put in x is equal to 3, I'm going to get 3 squared. Sorry, if x is equal to 0, I should say. If x is equal to 0, I'm going to get 0 minus 9, which is going to come out as -9. So that should be from -9 up to infinity. Okay, now the domain of this function here, well, x is allowed to be anything so long as it's not a negative number. So from 0 up to infinity is perfectly acceptable. And what's the square root of 0? That's just going to come out as 0. So our range is also going to be from 0 to infinity. All right, so next up, we need to determine the rule of the function f of g and state its domain. So to start this one out, we're just going to consider what this notation means. So what it means is f with an input of g substituted into it like this. So if I take the function f, that's this one here, substitute in g instead of x, I'm going to get, well, we've got this function. So I should say we're taking this function, we're putting in g, so it's g squared minus 9. And what's g equal to? Well, g is equal to the square root of x. So we're going to replace x with the square root of x. And our answer is going to come out as x minus 9, because when we square a square root, those two things cancel out. So we get f of g is equal to x minus 9. Now, the question is, does this actually exist? So does the square root of 9, so the square root of x squared minus 9, which is x minus 9, does this function exist? Well, how can we check? So in order for a composite function to exist, the range of the thing on the inside, so we're going to put in a value of x, we're going to get out a value from g of x, so that's going to be our output of the internal function. That output is then going to be the input for the external function. So that means that the range of g needs to be a subset of the domain of f. So let us consider the range of g. So the range of g we found before to be this, and the domain of f is r. So we need to ask ourselves, is 0 to infinity, is that a subset of r? Yes, it is. Yep, so 0 to infinity is part of the real numbers, so therefore it does exist. So yes, it exists. Okay, and then what's the domain of this function? So here's something that we need to realize here. F is only going to be defined if like we get like a value of x that is valid, that is going to come out of g. Now, if we think about it, there are certain values that g cannot take. So, for example, g cannot be a negative number as its domain. So we can't put in, say, for example, -1, because then we're going to get the square root of -1, which is going to be an imaginary number, so it's not going to be defined. So that's not allowed for the square root of g over here. The square root of x, sorry. So that tells us that although we have this function, because this is something that might confuse you, f of g is equal to x minus 9, you might look at that and say, well, obviously that's defined for every single value of x. That's just a linear equation, so surely the domain is r. It's not r. So remember, with even though the square root and the square cancel out, if this is the square root of a negative number, that's our output from g of x. That needs to be defined. Like g of x needs to be defined. So because g of x is only defined for x greater than or equal to 0, that's going to be the domain of our function. So domain needs to be greater than or equal to 0 as well. So the domain is going to be x larger than or equal to 0. So not all of the real numbers, in other words. All right, so now we say let h be the function d to h of x, where hx is equal to x squared minus 9. So this is like f from before. We need to determine the maximal domain such that h of g exists. So g of h, I should say. G with an input of h of x. So when will this exist? When will this exist? Well, this will only exist, if and only if. So it will exist if and only if the domain, sorry, not the domain, the range of the thing on the inside needs to be part of the domain of the thing on the outside. So the range of h needs to be a subset of the domain of g. So let's consider what each of these things are. Now, g is not being affected, so g is just this here. What is the domain of g? Well, the domain of g is from 0 to infinity. And currently, our unmodified version of f, what's that one's range? Well, the range of f is from -9 to infinity, isn't it? So is -9 to infinity a subset of this? Well, no, it's not, because negative numbers are not a subset of the positive numbers. So we're going to have to somehow restrict this domain. So that means we need to restrict. So we need to restrict h of x such that its output is going to be from -9 up to infinity. Sorry, not from -9, from 0 to infinity. We want to restrict it so that it can be part of our domain of g of x. So how can we do that? Well, that tells us that x squared minus 9, so x squared minus 9 being the rule for h, x squared minus 9 needs to be greater than or equal to 0, which tells us that x squared needs to be greater than or equal to 3. Sorry, x squared needs to be greater than or equal to 9. I'm jumping ahead of myself there. Then if we square both sides, we're going to find that, well, there are two possibilities, right? We could have a positive root and a negative root. So you need to be really careful here. With the positive root, we're going to get 3. So 3 times 3 is 9. So square root of 9 is 3. But this could also be -3. So if this is equal to -3, then x needs to be less than or equal to -3. So have a think about that. If x is, say, for example, -2, -2 squared is equal to 4, which is not larger than 9. So these are our two requirements. So that tells us that x needs to be an element of the numbers from -infinity up to -3, union with 3 up to positive infinity. So those are our requirements for g of h to exist. And what about our requirements for h inverse to exist? Well, the inverse of this function here will only exist if the function is 1-to-1. So the inverse of a function only exists if the function is 1-to-1. So we'll just do it up here. Inverse exists if and only if h of x is 1-to-1. So how can we restrict the domain of this function so that it is a 1-to-1 function? Well, we're going to have to cut it off at the turning point. So remember, this graph, it looks like a parabola with a turning point at 0, -9. So if we make the domain from 0 to infinity or from -infinity to 0, then we've just got a straight line that passes both the vertical and the horizontal line tests. So therefore, we can restrict the domain to be from, say, for example, -infinity to 0 inclusive, Or, so there's two possible solutions here. X could be from 0 up to positive infinity. So either one of those will work out perfectly fine. All right, moving on to this question here. Question 2, transformations. Now, what we're required to do here is state the transformations that have been applied to the equation y equals x squared to create this equation here. Now, this sort of transformation question can be very tricky. Now, what I want you to go through whenever we're naming transformations, the first thing you probably want to do is get your function into standard form. So we can see we've got this x squared function. To write this in standard form is to write it in the form of y is equal to f of whatever the, sorry, I should say y is equal to some number a, so our dilation factor that's affecting the y coordinate, times the dilation factor affecting the x coordinate, minus h plus k. Get it into this form with the x by itself inside of some sub-brackets with the common factor taken outside there. So specifically for this example here, we're going to write this in the form -3 of 2. We take out the 2 inside the square, and we get x plus 3 squared minus 7. You can see they're equivalent forms of one another, but this is going to more easily allow us to see where the dilation, translation, and reflections are. So you can see we've got a translation of 3 units in the negative direction, when you might accidentally say that that's 6 units in the negative direction. So first do this just so you don't make that kind of error. All right, now we're going to go through the procedure. What you want to do is start out by naming the dilations that are affecting your function, then the reflections, then the translations. The way you remember this is DRT, so start with dilations, then reflections, then translations. All right, so I'm going to use Desmos to help us visualize this. So we start out with the function. So we're going to start out with the function y equals x squared. All right, so that's this function right here. And what we want to do is keep track of a single point that lies on that graph. So I'm going to choose the point 1, 1. Okay, so let's think about what happens to turn this graph into, say, y equals 3x squared. Okay, so there's that 3 at the front here. That's our first dilation. What happens here? So we can graph it to see what happens to it. Well, what is happening is we're taking our value that we're going to get from the function y equals x squared, and we are multiplying that by 3. So what we're doing here is we're taking the old coordinate, the old y value, we're multiplying that by 3, and we're getting the new y value. So that means that the new y value is equal to 3 times the old y value. This is what is called a dilation by a factor of 3 from the x-axis or parallel to the y-axis. These are the two ways you can think about it. So here's our point, 1, 1. What happens to it? Well, it gets multiplied by 3. It ends up here. It's 1, 3. Okay, so that value, y equals x squared, x was equal to 1, so 1 squared. We're taking that value, we're multiplying it by 3 in this equation, y equals 3x squared, and now it's the point 1, 3. What happened to it? Well, it got stretched, right? Like it was down here at 1, 1, it's been moved up, and now it's at 1, 3. So it's been moved away from the x-axis in the direction parallel to the y-axis. So that's what happened to it there. All right, moving on. So that's how we describe that first transformation. Let us now consider the next transformation. So what we could next consider is, say, for example, this translation. I know we said DRT, but I've just done this on Desmos before like this. It doesn't really matter. Reflections and translations are very similar to one another. So how do we get the equation y equals 3x squared? Well, let's plug that into Desmos. What are we doing to it? Well, we're flipping it, right? What do we mean by flipping it? This is called a reflection. We are reflecting it. Are we reflecting in the x-axis or the y-axis? Well, you can see the x-axis is the mirror about which it's being reflected. So we say that this is a reflection. This is a reflection in the x-axis. So we've taken the old y coordinates and we've made it negative of the new y coordinate. Or we can say that the new y coordinate is equal to negative of the old y coordinate, and this is called a reflection in the x-axis. Okay, next one. So let's take that function now. How do we get what we've got here? Well, what we've got, oh, by the way, that gives us this point over here. So the point is now down here at 1, -3. That's the same point that we're keeping track of, okay? Now, getting back over here, next thing that happens is we've got this 2, so we want to do all the dilations and reflections to start off with. So how do we create the function y equals -3 2x squared? How do we do that? Give myself a bit more space for this. So this is probably the one that confuses people the most, because it's the dilation in terms of x. So this is y equals -3, and we're going to replace x with 2x squared. So don't worry about the +3, don't worry about the -7. We just want to work out, how do we create this equation? Well, what have we done here? We have taken the old x coordinate, this one here, so the old x coordinate, the one from step 3 here, and we've replaced it with 2x. And what's this x here? Well, that's the new x value, okay? So what has happened to create this new x value? Well, what we can do is we can maybe rearrange this equation in terms of the new x value. So the new x value is equal to a half of the old x value. You can see we divide both sides by 2. So what's happened to create this new x coordinate? We've gone and we've taken that old x coordinate and we've divided it by 2. So what we call this is a dilation by a factor of half away from the y-axis. You can see this if we type in this equation. So this is this one, y equals -3 2x squared. What we've got is that there's that same point, right? What's happened to it? Well, it's gotten closer to the y-axis. So this is a dilation by a factor of a half from the y-axis. So from the y-axis, which is the same as the direction that is parallel to the x-axis. So this is a dilation by factor a half from the y-axis, which is the same as parallel to the x-axis. Keep in mind that you need to use this language. You can either say dilation from the y-axis or parallel to the x-axis. VCAR will not accept anything else. It needs to be one of these, so choose which one you're going to use. You could also say dilation by a factor of a half from the vertical direction or parallel to the horizontal direction. That's also valid, but you can't make it abstract. You can't say like dilation in the x-axis. Like, what does in the x-axis even mean? You need to say parallel to or from. Very important. Okay, so now I've got this equation here. What's next? So the next two are pretty straightforward for most people. We're going to take that equation now, and we want to create the equation y equals -3 2 times x plus 3 squared. Okay, so now what have we done here? Well, we've taken the old x coordinate, or the old x coordinate, and we've replaced it with the new x coordinate plus 3. There we go. We've taken the x value there, and now instead of being x, it is x plus 3. So if we rearrange that in terms of the new x coordinate, what we've really done is we have taken the old x coordinate and we've subtracted 3. So this corresponds to a translation 3 units in the negative x direction. So you can see if there's a plus there, it's actually going in the negative direction. So this is a translation of 3 units, or by a factor of 3 units in the negative x direction. You could also say to the left. So here it is. Here's our graph. Okay, y equals -3 2 times x plus 3 squared. Where's that point? There it is. Let's label it. So it started out over here, and now it's been moved, and now it's over here. So you can see it's been moved 3 units to the left. All right, final transformation. So almost done with this one. We need to create the equation y equals -3 of 2x plus 3 squared minus 7. So this is our final equation. What are we doing to create this equation? Well, we're taking the old y value. So this is the old y value, and we're minusing 7 from it. So you can see the new y value. So the y new is equal to y old minus 7. Simple as that. So this is a translation of 7 units down. So translation 7 units down, or you can say in the negative y direction. And what does this graph look like? Well, it looks like this. And what happens to that point? Well, the point is now down here. So the point was there. It's been moved down to negative 10. Okay, and it has not affected the x coordinate, as you can see. So that's the graph, and that is how the transformations have affected it. So overall, I mean, obviously, in a real exam, you're probably not going to get this many transformations happening, but in order, and order really matters here, because otherwise we're going to get a different result. So we're going to list out the transformations. We can say that the equation y equals x squared undergoes a dilation by a factor of 3 from the y-axis, followed by a reflection in the x-axis, followed by a dilation by a factor of a half from the y-axis, followed by a translation of 3 units in the negative x direction, followed by a translation of 7 units down in order to create the equation y equals negative 3 of 2 times x plus 3 squared minus 7. So hopefully you just understood that sentence that I just said. If you did not, maybe just go back over and revise transformations because it is super important. It comes up in every single exam. All right, let's try and wrap this up as quickly as we can. So we're now going to take this function here, and we need to determine its inverse function. And I'm very aware that these exam questions were probably longer than ideal. Probably could have just given me that one from before and that would have been enough. But let's just wrap these two up. So how do we do inverse functions? All right, what we need to do for an inverse function is we are simply going to swap the y value and swap the x value and then solve for y. So here's our equation. Y equals square root of 2x plus 1. All right. We're going to take that y value and we're going to swap it with the x value. So we're going to swap it, write it as 2y plus 1. Okay, so this is the inverse. And therefore, we're going to rearrange this. We're going to first square both sides. We're going to minus 1 from both sides. And then we're going to divide both sides by 2. Okay, so hopefully everyone can do this. This is the rule for the inverse function. We need to also state the function in function notation, and I reckon this is where a few people may have gone wrong with this question because it's a little more subtle than you might realize. So first up, this equation here, y equals f of x. F of x is equal to this function here. Let's just think about its domain. So the domain of f, what's its domain? Well, this thing underneath the square root can't be 0, which means that 2 times x can't be less than 1, because if it was, say, for example, less than negative 1, if it was negative 1, then we'd get negative 1 plus 1, which would be 0. If it was negative 2, we're going to get negative 2 plus 1, which is negative 1. That's going to be a negative number. Shit. So what are we going to have to do then? Well, what we'll have to do is we'll think, okay, x needs to be larger than or equal to maybe a half. To work that out, we can just think 2x plus 1 needs to be greater than or equal to 0. So therefore, 2x needs to be greater than or equal to negative 1, which tells us that x needs to be greater than or equal to negative a half. So the domain of f is going to be from negative a half up to infinity. The range of f is going to be from 0 to infinity because a square root can never give us a negative answer. Now, something that we need to realize is the inverse function, the domain of the inverse function is equal to the range of the original function, and the range of the inverse function is the domain of the original function. So therefore, the domain of f inverse is going to be the range of this function here. So therefore, when we state it in function notation, we need to include this as our domain. So our inverse function will come out as, so we write it in to write this in function notation, we start by naming the function. So f inverse, we give the domain, so 0 to infinity, to r, so this is always going to be r, the codomain, of f inverse of x is equal to x squared minus 1 over 2. That is the answer to this question. So make sure that you got the domain right for that. That's the subtlety. All right, final question. So let's see if we can work out how we deal with these transformations. So the question says we're going to start with the function f of x is equal to square root of 2x plus 1. This undergoes a dilation by a factor of a half from the vertical axis. Let's think about what that means. From the vertical axis, this is the vertical axis here. It's going to go like this, moving like that. Dilation by a factor of a half. What's that affecting? Is that affecting the x value or the y value? Well, it's affecting the x value, right? Like it's not being moved up and down, it's going left and right. So what's happening is the new x value is equal to half of the old x value. That's what by a factor of a half means. What we have here is a formula for sorry, what we have here at the start, we're taking, this is the function. So we're starting with this function f of x. This is the formula for the old x value. So we're going to replace that old x value with the new x value. How are we going to do that? Well, first we need to rearrange this equation and get it in terms of the old x value. To do that, we can multiply both sides by 2. If we do that, multiplying both sides by 2, we get x old is equal to 2 times x new. Now we can replace the x old in this formula with this 2x new. The formula will become, after our after our transformation, so let's just call it the f of 1, or maybe we can call it g of 1, it doesn't really matter. G of 1 is going to be equal to that old f function, but we're replacing x with 2x, and that's going to give us the function 4x plus 1, all right? Now, what happens next? We're translating 2 units to the right. So that means that the new x value is going to be equal to the old x value. We're moving to the right. That's the positive x direction. So it's going to be plus 2. And we want to rearrange this in terms of the old x coordinate. So it's going to be the old x coordinate is equal to the new x coordinate minus 2. What we have here is an equation for the now old x coordinate. And we're going to create the final function, so gx. That's going to be equal to that function there, but we are going to replace the x value with x minus 2 plus 1. All right, so now we've got this function here. We can expand those brackets. That's going to give us 4x minus 8 plus 1. And if we collect together these like terms, that's going to be equal to 4 times x minus 8 plus 1, which is equal to minus 7. And that there is our final function, g of x. All right, so like I said, those were some pretty challenging questions for this week's exam-style problems, but hopefully this little video helped you revise and understand transformations, inverse functions, and composite functions. Hopefully this was helpful. I'll catch you guys in class. Have a good night. See you next time.